right, let's look at, oh dear, let's look at some velocity time equations, okay? Or sorry, I should say, actually, let's just go with this, velocity equation. Now we've touched on this, but we haven't actually formalized it, I don't think, into pure values, and I just want to make sure that we can solve some problems with this. So V, velocity. Now I'm going to draw a little arrow on top, just to remind us that velocity is a vector. Velocity is found by looking at the change in displacement divided by the change in time. Is time a vector? No, it is not, right? Time only goes in one direction. So we find velocity as the change in displacement divided by the change in time, okay? Let's do a quick example and solve. Example. Find the velocity in meters per second and kilometers per hour for a vehicle that starts at 10 meters at 4 seconds and is at 110 meters at 6 seconds. Okay. So I'm going to draw a quick little pic of this while you're writing that down. Okay. So there's 0 meters. Here's 10 meters. 20, 30, 40, 50, 60, 70, 80, 90, 110, 110 meters. This is the initial position. This is the final position. And this happens over a time interval, which starts at 4 seconds and ends at 6 seconds. And there's all of our information. Okay. So before we actually do any solving with this, I want to draw a little graph of this so that we can just help ourselves understand what's going on. Okay, so let's just, I just want to quickly draw a graph of what this motion might look like. Okay, so we know it starts at 10 meters. It starts at 10 meters and goes to 110, and that happens between 4 and 6 seconds. Okay. So we'll get something like this. Now, one thing I just want to be careful of here is actually just watching what we're doing with time, right? So this actually would be where our 4 second is, 5 second, 6 second, 3, 2, and so on back there. So in other words, probably what's going on is we didn't start, or we started our timer before any motion happened, or something's going on where our timing and our motion are not starting at 0, okay? And that's okay. That's not a problem. We can still deal with that. So let's just review here. Okay, so this is at 10 meters. Here's 110 meters. And let's use this little formula to solve for this velocity of this object. Okay. Okay, so we got a couple of input values. Here's our initial position. That's at 10 meters. And our final position is at 110 meters. Our time initial, TI, is at 4 seconds. And our final time is at 6 seconds. So I feel like I'm just beating this to death. But let's apply our formula and sort out what's going on here. So the velocity then is actually going to be the slope. It's going to be the rise over the run. The rise is the change in position, or for the sake of the formula, we're actually going to call it D, okay? Even though it's a change in position, the actual delta, this is the actual displacement, but what we need is we need the difference between the two. So we'll use the values that are, or the symbology, I guess, that's given to us. and delta t. So put in your values. Delta d represents final minus initial, so 110 meters minus 10 meters divided by 6 seconds minus 4 seconds. If we write that out, we should get 100 meters, and you go 100 meters in a total time of 2 seconds. And some quick math should give us 50 meters per second is the velocity of this object. Okay? Does that make sense? All right. So the second part said to list this in terms of kilometers per hour. We're much more used to dealing with kilometers per hour, I think, in our daily lives. So how are we going to go about switching this over? So what we have is we have a velocity that's going 50 meters every 1 second. Okay? So if you look on the top, there's meters, and you look on the bottom, there's seconds. So let's convert the top into kilometers first. Okay? Does that make sense? Should we do that? Okay, so how do we do it? Yeah. Okay, sure. We divide it by 1,000 essentially, right? But I'm going to show you a slightly different way to do it. Okay? I'm going to use multiplication here. Okay? Don't let this blow your mind. Just watch the magic. Okay, so what do we know? We know that for every 1 kilometer, and you'll notice I put kilometers on the top because that's where I want kilometers to be, right? We want this in terms of meters. For every 1 kilometer, we have 1,000 meters. Okay? So if I take 50 over 1 and multiply by 1 over 1,000, essentially what I'm going to do, if you look, if I multiply the top over, let's see, 50 meters times 1 kilometer, right? I multiply what's on the top, and I multiply what's on the bottom. Well, I'll take a look here, right? I get meters here, so my units are meters, divided by another unit in meters. Well, my meters themselves are going to cancel out. 1 times 1,000 is just 1,000. 50 times 1 is just 50. So I get 50 over 1,000 kilometers every second, or 0.050 kilometers every 1 second. That make sense? Sort of. Kind of. I'll show you an easier way after this. Not even an easier way, just a slightly different way after this. But that doesn't really help. That's only saying we're going 0.050 kilometers every 1 second. So we got to convert this over to be in terms of hours. What's that? Okay. Okay. So let's use the same idea here. Well, 1 second is 1/60th of a minute, isn't it? Okay, so we're going to say 60 minutes. So in other words, we're going to go 60 times this every minute. Does that make sense? Look and see. See if that makes sense. If we go half a kilometer every second, every minute we're going to go 60 times that, right? Every second, okay, in a minute is 60 times that. That makes sense, right? So multiply by 60 meters, 60 minutes, sorry. My bad. I'm talking too much and not thinking enough. What I really want to say is there are 60 seconds every 1 minute, right? So I'm going to go 60 times this. And then it's got to be even more than that, right? Because we don't care. Well, it might be interesting to know how far we go in a minute, but what we really want is how far we go in an hour. So 60 times this every second times 60 times that every hour. There's 60 minutes in 1 hour. Now let's see what happens here. 3,600 times 0.050. What's half of 3,600? 1,800 minus 1 0 minus 2 zeros. Oh, no. Is that right? I think it should end up being 180 kilometers per hour. 3,600 times 0.5 would be 1,800, right? Minus 0, 180. Okay. So we get 180. Notice there's kilometers on the top, but there's also seconds and minutes on the top. But look, there's a seconds on the bottom and a seconds on the top. a minute's on the bottom and a minute's on the top, and we're left with hours on the bottom. 180 kilometers every 1 hour, or 180 kilometers per hour. All right, so maybe a little confusing. I don't know. Possibly slightly confusing. Is it? If not, that's excellent, but I'll just explain it to you one more time without writing all this stuff down. So hopefully you can really understand it. So if we have 50 meters every second, right? That's the same as saying, well, 50 meters, 0.05 meters, kilometers every second. Right? Yeah, that's right. Okay. And then if we go 0.05 of a kilometer every second, right? We know we go 60 times that much in a minute and 60 times that much in an hour. 60 times 3,600. So half of that is 1,800 divided again by 10, right? To move it back one more. That's how we get our 180 kilometers per hour. Okay? So that's a way to convert between two, kind of different units. All right, let's try one more, and then I'm going to let you go to work. Last one. How far would this person travel in 4 hours? Okay, so remember, velocity equals delta D or delta T. Okay, now we're interested in how far the person's going to go or what their change in displacement is going to be. So we need to isolate for what we're interested in. This is our unknown. Okay, so we're going to have to do some algebra to get our unknown on its own. Okay, so I'm just going to really quickly write this without the deltas in place. I want to get the t off the bottom. So I'm dividing by t, so I need to multiply by t. And what I do to one side, I have to do to the other side. So if I multiply this side by t, divide by t, then multiply by t, cancels t. Since I multiply by t, that has to go over onto this side. So I get vt equals d. And if they're equal, I'd probably rather just write them like that. Displacement equals velocity times time. So look at what we have here. We have displacement equals a velocity of 180 kilometers every hour, because we just figured that out. And we said it does this for 4 hours. So 180 times 4. Well, 4 times 100 is 400. 80 times 4 is 320. 720. 360, yeah, that works too, right. Multiply by 2 twice, right? So that also works, sure. Multiply by 100 times 4 is 400 times 360, add them together. 20, I should say. And you get 720 kilometers.